All right. Hello, everyone. Firstly, I wanted to thank everyone for making it all the way to the end of the conference and sticking around. Thank you. My name is Ahlad Neti. I am a third-year PhD student at the University of Pittsburgh. I work at the Human Engineering Research Laboratories with the Department of Veterans Affairs. And today I'm going to be talking to you a little bit about my research, or part of my research, which is the type and intensity classification of different activities of daily living for manual wheelchair users. First and foremost, just wanted to say no conflicts of interest to disclose, and our grant funding for this project is from the Craig Nielsen Foundation. Firstly, our lab and our Human Engineering Research Laboratories in Bakery Square and some of our faculty members are listed here. We're more than happy to collaborate with various projects in different institutions, so feel free to reach out if you're interested. Quick agenda and so currently in the United States, there's around 5.5 million manual wheelchair users, and the majority of these rely primarily on their upper extremities for all aspects of their life, whether it's transfers, propulsion, hygiene, different activities of daily living like folding clothes, washing dishes. And a lot of these loads, when done improperly, or a lot of these tasks when done improperly, can introduce large loads on the upper extremities, specifically the shoulders, elbows, and wrists. When doing a lot of these tasks frequently and improperly, it can lead to pain and discomfort either in the short term or the long term. In the long term, this can lead to decreased quality of life, decreased independence, more reliance on a caregiver, and generally lower quality of life. So what we want to do is analyze these activities of daily living. How often are people performing these? What level of intensity are they performing them at? And are there differences among different populations performing larger frequency of high intensity activities? Does it expose you to more injury than a sedentary lifestyle? But there is that, balance of how active do you want to be versus how safe do you want to be? So we know that these activities of daily living can cause upper extremity pain and discomfort. So we want to analyze the frequency and the intensity of these. If we're able to identify when, where, and how they're occurring and inform either the wheelchair user, the clinician, or a caregiver about these tasks, they're going to be able to modify their actions, change their intervention plans, and hopefully improve the long-term health of the wheelchair user. So the first step in that is being able to identify and classify these tasks in a real-world environment. And so that's kind of what we're planning on doing in this project. In the past, there's been a lot of work done on activity recognition. This has been mainly through motion capture research. However, these are very expensive systems and they require very permanent setup in the lab. They're very accurate, and so they've had a lot of success in being able to identify various different activities, whether it's transfers, propulsions, walking, running, lifting tasks, etc. There's also been work done with wearable sensors such as IMUs and EMGs. However, this activity recognition has been limited to general classifications such as propulsion and non-propulsion tasks, or caregiver and non-caregiver tasks. It doesn't really break it down specifically into the type and level of intensity. Going on with that, the loading demands of these activities has not really been analyzed, as in there's not been an analysis on the different levels of the same activity being performed, such as if you're performing an overhead reach with lifting 5 pounds versus lifting 10 pounds, it's going to exert very different amounts of forces on your joints. So the objective of this study was to develop, train, and validate machine learning classification models to identify the type and intensity of activities of daily living with wearable sensors. And so there's two hypotheses. These just kind of break it down into the being able to identify the activity and being able to identify the level of intensity that it was performed at. We're going to be using inertial measurement units and electromyography sensors. These kind of measure the orientation of different body segments and the amount of effort different muscles are contributing. And we're going to use a general threshold of 70% accuracy as a successful model criteria. There's a lot of other different parameters that go on in machine learning, such as F1 score, and area under the ROC curve. We're going to be analyzing these as well, but the general threshold of 70% is kind of used across the board in machine learning. So for this, we are targeting 30 manual wheelchair users, and the kind of main inclusion-exclusion criteria I want to point out are they have to have been had a spinal cord injury diagnosis for at least 12 months, have moderate chronic neck or back pain, and have no history of dislocations or fractures in the upper extremity. This is just because we want to prevent any additional injury to our participants. So we have our participants perform 6 different activities of daily living at 3 different intensity levels. I'll go on to what these are specifically in a little bit. While they're performing these tasks, we're going to have a total of 13 sensors attached onto their body. There are 8 electromyography sensors attached to the biceps, triceps, the anterior deltoid, and the pectoralis major on both the left and right side. These measure the general activity of the muscle, and so we normalize this with what's called a maximum voluntary contraction, where we elicit 100% signal, and then during the trial, we're able to say, oh, you used 20% or 30% of your maximum effort. Additionally, we use inertial measurement units, which are a combination of accelerometers, gyroscopes, and magnetometers. These work together to give us an orientation estimate of the different body segments. These are going to be attached to the forearm, the upper arm, and there's going to be one wrapped around the sternum. These are going to be calibrated with a global reference sensor. So we have one sensor on the ground that acts as our gravity reference. That way, all of our sensors are going to be able to be related back to our global frame, and we don't have to worry about any individual rotation matrices between sensors just to save on different calculations. Here are the different activities that they perform, broken up into the 6 general classes and then the 3 different intensity levels. There is paperwork. This was kind of used as our baseline, kind of no activity, very, very stable action. There's obstacle course propulsion. I'll go over what our obstacle course was. There's overhead reach, the folding of clothes, performing level and non-level transfers, and different types of pressure relief. You'll notice that not every type of activity has an action for each intensity level. This is just because some activities generally are either more or less intense than others, such as paperwork has no moderate or high intensity activities, whereas we consider transfers and pressure relief to be high intensity, so there's no low intensity version of that. Generally, with the overhead reach and the folding of clothes, or the overhead reach and the obstacle course, we're able to separate that out into the 3 different levels. Here are the different obstacles that we tested in that obstacle course, once again broken down into that high, moderate, and low intensity regions. There's a high pile carpet, low pile carpet, a small rubber mat, this is texturized. There's a slap board, a small speed bump, a foam board, which kind of simulates grass or sand, and then an incline to a 4-inch curb drop and a small gravel board. This obstacle course is very similar if you were in the previous presentation and you saw that one. It's the exact same course. This is the order it was laid out in. It was the exact same order, same dimensions, same positioning for every single participant. This is because we wanted to keep the order of going low, moderate to high in order to reduce the amount of order effects that it would occur. So once we collect all this data, we have those 13 sensors. We have a bunch of different signals coming out from each one of those. And then we want to analyze different features out of those, both time and frequency domains, as averages, standard deviations, frequencies, peaks, and all of those. We're then going to take different segments, times of windows. For this study, we used 5-second windows. So we took 5-second windows with our time series data, pulled out all of our features from those, and then labeled each window with an activity classification and the intensity classification from where the activity was performed. We then performed an F-test on all of the features. This was just kind of to see generally which features were more significant in determining differences between the activities. This gives us an idea of which features to use for our later on machine learning. Then we did some dimensionality reduction and then some actual training of the models, which I'll get into. Just generally the machine learning models that we decided to use. These were chosen based on a literature review. These have been very successful in other activities of daily living. Identifiers in various studies, both in able-bodied and in individuals with disabilities, broken up into both the linear and nonlinear just because they are 2 forms of classifiers. So far, we've collected 12 participants, and their average about 42 years. We've had 9 males and 3 females. And kind of the other important demographics I want to point out are years of using the wheelchair, the amount of experience. It's about 18 years with a very high standard deviation of 14, meaning we have a wide range of experience, which is very good for our study because we're able to get hit our target population and kind of represent it a little bit better. And also because we're doing activities of daily living that require kind of dominance on hand, we also recorded hand dominance. 10 of our subjects were right-handed, 1 was left-handed, and 1 was ambidextrous. It's kind of an overview from the feature importance. I have the individual values. If you're interested, I can talk about what they are. For the activity, it was mostly the IMU features. This means that it was mostly body segment orientations and movements that were different between the different activities that were classified. Specifically, the forearm and the upper arm were more significant than the sternum, which makes sense since those are generally going to be more active. The intensity classification, there was a large mix of IMU and EMG signal. This makes sense because a larger intensity would require a larger activation of your muscles. So we would expect to see higher values for a higher intensity classification. These were generally less significant. They had lower statistics values than the activity features. And I'll get into this in a little bit. It just seems like it's going to be a little bit harder to distinguish between the different levels of intensity than the different activities that were performed. And with that intensity, since we expect the EMG signal to be higher at higher levels of intensities, we're able to perform a post-hoc analysis. And we've proved that with a very high significance level, that the low intensity had significantly lower EMG signal than the moderate or high intensity, specifically looking at just the right pectoralis muscle. But this was kind of true for all the muscles. This is just an example. Next, we go into something called dimensionality reduction. This is to go from our high dimension space into a low dimension space. Generally, this is preliminary analysis done to see how our data looks, how successful it's going to be. And there's multiple versions, linear and nonlinear methods. You see here is, since we have around 1,099 features coming from all of our 13 signals and all of our different features, it can kind of mess up and cloud the data. So we do this in order to see if we can go from 1,000 features to 5. That's going to be a little bit easier to sift through both for us and for the computer. When plotting those values, we see here that with at least principal component analysis, which is a linear dimensionality reduction method, we don't really see any clusters. We see no separation of colors. It's very hard to see any differences here. Therefore, I don't think that a linear method is going to be successful. When we look at a nonlinear method, that's a very long name, it's abbreviated TSNE, we see a lot of very dense clusters. And so here, each of the different colors are a different activity classification. This was just throwing in all the data. It wasn't trained or anything. This is just what the computer was able to differentiate out in a nonlinear method. So we see a lot of clusters here of some propulsion tasks, but they're kind of all over the place. They're not very centered. When we look at intensity, we see why it was harder to differentiate intensity. There's a lot more overlap between the colors, because between a high intensity propulsion versus a high intensity pressure relief, it wasn't as easy to differentiate between in the signals. And lastly, I just decided to do one other linear method just to see if PCA just wasn't working as well. This is linear discriminant analysis. That's a typo. Here we see very good separation of colors, very good density. So this is very good support that we might be able to accurately identify activity. Intensity, on the other hand, we see some kind of separation of the colors, but there is a lot more overlap there in the middle, which we can once again kind of get some idea of where we're going to be going in our models. We then performed the actual model training. This was done with a leave one subject out cross-validation method. This is because when we eventually take this to the real world application, we don't want, we want to be able to extend it to all subjects. We don't want it to identify just one subject's propulsion versus activity and not be able to work on another. So what we do is we take one subject out, train on the rest of the subjects, and then test on that remaining subject in order to ensure that it's going to be valid. Therefore, a lot of the values I'm reporting here are going to be the testing accuracies, and this is averaged over all the different subjects that were then left out. And so we're able to get a good representation of how it was performed. We tested various different windows and different sets of features. I'm going to be presenting 5-second windows with 50% overlap. And then we tested all the features. We tested just the time series features and then just the right side. This was because time series features are generally faster to extract. And so if we want to put this into a real world, real-time setting, it's going to be faster analysis. And we did right side only because generally in the real world, if you were wearing any sort of sensor technology, such as I'm wearing a watch, I only have it on one side of my body. I'm not having it on both sides. We reported accuracy scores generally, random forest classifier and linear discriminant analysis, which is actually the visual that I showed, performed the best out of all the different models. Here we can see the general percentages. We are mostly just looking at between here to here to here to see the different sets of features, the different rows of the different models, and then activity versus intensity. From here, we can see intensity had lower testing accuracies than the activity did, which kind of goes based off of what we saw earlier in dimensionality reduction. And RFC had generally higher levels. That 70% cutoff was met at the activity, not necessarily the intensity. Now, this was done with what's called a multi-class classification. So the model is trying to predict all 9 classes at the same time. There's another method called leave one versus rest, where it tries to predict just propulsion against everything else, just transfers against everything else. When we did that analysis, it did improve the accuracy slightly, which means that we might have better luck creating individual classifiers for each activity that's performed. This would just kind of create a little bit more processing time, but if it gets us a better accuracy in the end, it might be worth it. So from our F-test, we can see that there are definitely significant differences between the features in both activity and intensity. The different levels of those differences are still kind of being analyzed as we collect more subjects. Dimensionality reduction shows that nonlinear techniques might be more beneficial, but in general, we might just have better luck using just the raw data instead of reducing the number of dimensions, since we had very high accuracies, at least in activity. One other thing we can explore is a 2-step classification. So first we classify the activity, and then we use that as an additional feature to classify the intensity. That might improve the accuracies we're getting for intensity. That still needs to be explored. And then with the along with that, we also want to be mindful of overfitting the models. If we're getting like 100% in either the training or the testing accuracy, that's a little indicative of something going wrong. Either there's too much noise, too many features. So we want to avoid that. That's why there were some models that hit 100% training accuracy. I did not report them because their testing accuracies were then at 2%, meaning that they would not be good for a leave one subject out cross-validation. In the future, we're going to keep testing different, more subjects, test different windows, overlaps, test the different balance between IMU and EMG signal. One thing we're interested in is using just IMU, since most cell phones and smart devices now don't really track an EMG signal. We're also going to do hyperparameter tuning of the models. All the models were just trained on their default parameters. However, each of them has various sets, and so it's called a grid search, kind of iteratively searches through every single one and gives you the best parameters out for your specific case. We'll also investigate deep learning and neural networks using just the raw data instead of the time and frequency domain extracted features. This is shown to be very well in the literature, but it requires a large amount of processing time, and so it might not be as suitable for a real-world application. Additionally, like I mentioned before, we'll also be looking at the F1 score, area under the ROC curve, as we analyze the different classifiers and as we move on. So generally, we have high promise of being able to identify activity. And so from this, we can then, the long term would be to create some sort of monitor that a wheelchair user can have that's going to be able to alert them, hey, you've been performing a large amount of high intensity propulsions in the last hour. Think about taking a break. Or you've been doing a lot of overhead reaching. Maybe you should stop doing whatever activity is you were doing and go do something else, or stretch or exercise or something we can train different intervention methods from the clinician side. It's also going to be educational for the wheelchair user side. And with that, that's all I had. So I'll take any questions if there's time, or 1 minute for questions, apparently. Yes. That was not mounted on the wheelchair. That was actually left on the ground. This was to establish kind of like the global gravity reference, because sometimes when they were performing a propulsion, an individual would perform a wheelie. If we had it mounted on the wheelchair, that would then change the orientation of our global reference frame, which we wanted to avoid.